Okay, so today we're very happy to have Richard Nally from MIT, who will be telling us about candidate de Sitter Vacua.
Thank you for the introduction and thank you for having me. It's very nice to be here. So I'm going to be telling you about a recent paper with Leah McAllister, Jakob Moritz, and Andrea Schachner, where we think we constructed some de Sitter Vacua of string theory. Yep. So they are my collaborators. So one question that sort of lies at the heart of string phenomenology, and the question that I'm going to make a small step towards addressing today, is, does string theory have vacua that look like us? Does our universe look like it can come out of a solution of string theory? And the answer is we have no idea. String theory is supposed to have this mind-bogglingly large number of solutions, and there's too many of them to actually construct them. So it's hard to say what properties the bulk of this distribution has. So let's bite off a more manageable parcel. Does string theory have de Sitter vacua? There's an experimental fact about our universe that not only is it expanding, the rate at which it's expanding is increasing over time. The way you explain that is you say our universe is a positive energy density, and universes with positive energy density and nothing else are called de Sitter space. So question, does string theory have de Sitter vacua? It's really hard to build de Sitter vacua of string theory. The sort of best studied way we know of how to do it was given to us by Katru, Palo, Schlinde, and Trivedi 20 years ago, KKLT. They provided a recipe for building de Sitter vacua, but in the 20 years between KKLT and our paper, nobody had actually done it. Nobody had been able to pick a particular solution of string theory that fulfilled all of the steps of their recipe. So today I'm gonna make some progress towards actually doing it, towards building a de Sitter vacua along the lines I told you to follow. And in particular, we're going to, in a truncation of the effective action of string theory, actually do. So we're going to throw out a bunch of unknown corrections to string theory. Without those corrections, we have de Sitter vacua, and that's what we're going to talk about today. So the basic context for what I'm going to talk about today is type 2B string theory in 10 dimensions. So 2B string theory is a 10-dimensional theory of quantum gravity. And to make contact with our universe, we compactify 6 of the dimensions. We take them to be a special type of manifold called a Calabi-Yau manifold, which is a Ricci flat Kähler manifold. And what that means is it solves Einstein's equation in 10 dimensions. And the resulting effective theory you get in 4 dimensions after taking a product space and taking the 6-dimensional compact space to be very small has supersymmetry in 4 dimensions.
Richard, can I ask just a big picture question for you? Yeah. So the difference between this and KKLT is that KKLT said, here are a set of ingredients that if you put them together could give you a de Sitter vacuum. You're going to tell us precisely what those ingredients are, which Calabi-Yau, what the fluxes are, and that sort of thing? Or?
So they said, KKLT said, if you find a Calabi-Yau where you can do all of these things, it should give you de Sitter. We went through and found a Calabi-Yau where you can do all those things. Yeah. And yeah, feel free to interrupt at any time. Yeah. So there's a lot of different Calabi-Yaus, and every different Calabi-Yau you pick gives you a different effective theory in 4 dimensions. And the matter content of the Calabi-Yau the matter content of the effective theory depends on the topology of the Calabi-Yau. Depends on the number of holes of the Calabi-Yau of dimension 2 and dimension 3. And that determines how many fields you get. So if you give me a Calabi-Yau, I can give you a 4-dimensional theory of n equals 2 supergravity, but there's a problem. It has a lot of massless scalar fields. It has massless scalar fields corresponding to the moduli of the Calabi-Yau, which are some complex parameters you can adjust to change the size and shape of the Calabi-Yau in the same topological class. So there's 3 different kinds of moduli. There's complex structure moduli, which control the size of the Calabi-Yau. Or sorry, no, the shape of the Calabi-Yau. And there's Kähler moduli, which control the size of the Calabi-Yau. So you can rescale the entire Calabi-Yau, or you can blow up certain regions of the Calabi-Yau, or you can sort of rotate different cycles in the Calabi-Yau around each other, and that's moving around in moduli space. And then there's also the axiodilaton, which controls the coupling constant of string theory. In string theory, the coupling constant is a dynamical field. It's not just a number. But really, the axiodilaton, it's the string coupling, but it's also basically a complex structure modulus. So you can think of it as beautiful. So us here in this room, we don't have 100 massless scalar fields lying around. So we need to get rid of them somehow. We need to stabilize them. We need to induce a potential with the minimum for these fields so that I can stabilize these fields at their minimum and leave them there so that there's no massless scalar fields going around. The way you do this, the way we're going to do this, is we're going to add fluxes for the gauge fields in 10 dimensions. In 10 dimensions, you have gauge fields very much like E and M. And in the same way for E and M, you can have fluxes through spheres and you can have charges. In 10 dimensions, you can have branes, those are extended sources, and you can have fluxes for the gauge fields. And when you turn those on, you induce potentials for all your scalar fields. And one way of asking what is the space of vacua of string theory is what are the properties of the minima of the potentials you get from doing this? So the potentials you get, the garden variety ones, they look like this, they take this form. They're defined in terms of two auxiliary functions, the superpotential and the Kähler potential. And most of what I'm going to be doing in this talk is actually, well, most of what I'm not going to be doing in this talk, but we did in the paper, and I'm not going to tell you about, is computing these functions. These functions depend sensitively on the topology and complex geometry of the manifold, but by now we know how to compute them. They can be put on a computer and the computer will spit them out for you. An important thing to note is that everything in this function is determined by discrete data. You can pick one of a list of Calabi-Yaos, and you can pick integer fluxes through cycles in the Calabi-Yao, but you can't turn any numbers. You can pick integers, but you can never pick continuous numbers. And I think that's sort of the characteristic feature of string theory. It has no continuous parameters. It only has discrete data to pick. And you pick the discrete data and you get a potential like this, and you can try to extremize the potential. If you can extremize the potential, if you can find a minimum for all of the fields in your theory, then you've gotten rid of all your massless fields. You've stabilized the module. So that's the game we're going to try to play today. The simplest way you can do this is you can find what's called a supersymmetric minimum. In a supersymmetric minimum, a suitable derivative of this guy, the superpotential is 0, but the superpotential itself is not 0. When that happens, and you can stabilize all moduli, you land on a supersymmetric solution of string theory with negative vacuum energy. You land on a supersymmetric ADS vacuum, anti-de Sitter negative vacuum energy as opposed to de Sitter. So I say these are the simplest ones, but those were only constructed in 2021. The first examples where everything was really completely controlled. So they're simple, but they're hard. Importantly, oh yeah.
Quick question. So for the masses you get for these moduli, is there, like, should I expect the masses to be of the order of the string scale, or they're parametrically smaller?
They're going to be sort of intermediate. They're going to end up being larger than the scale of the ADS or de Sitter vacuum you get, but smaller than the string scale. So they're going to be heavy in effective field theory units, but not in Planck units. Other questions?
Would you tell how these moduli are stabilized, even at this supersymmetric point, in particular the axiodilaton?
Yeah, so I will comment on how we stabilize the axiodilaton. I don't go into too much detail, but I'm happy to tell you however much you want to know about it. The short answer is we work in a corner of moduli space where the flux superpotential takes a very particular form. Effectively, it becomes a one-dimensional theory where the complex structure moduli are parameterized by the axiodilaton. And then from there, it's a one-dimensional potential and you can just extremize it. Okay, so these simple solutions, which aren't really that simple, they're too simple to ever give you de Sitter. And that's because you can't have de Sitter solutions that preserve supersymmetry. So to get de Sitter, you need to break supersymmetry in some way. And the thing KKLT did is they proposed how you can break supersymmetry. They told you to break supersymmetry by incorporating the effect of an anti-brane. So much like you could have positive and negative charge in E and M, in the 10-dimensional gauge fields, you can have sources and anti-sources, and those preserve opposite supersymmetries. So you turn on some sources, you break one of the two supersymmetries, then you turn on the anti-source that preserves the other supersymmetry, but breaks the one you've already preserved. So now I've broken both of the two supersymmetries I started out with. I'm left with no supersymmetry. You can land on de Sitter. That was KKLT's idea, is that you first break one half of the supersymmetry and then the other, and then you win. You can use supersymmetry to help you, but you have to get rid of it at the end. And that's why we like KKLT more than most of the other proposals for how to get de Sitter out of a Calabi-Yau compactification, because you can stay supersymmetric for longer. It's nice to have supersymmetry as a tool, but you can't rely on it too much, and KKLT tells you how to use it to your advantage, and then get rid of it. So here's what KKLT told you to do. They told you to start at a supersymmetric ADS minimum with all the vacuum, with all the moduli stabilized. So you have a potential, and it might look something like this. You've got some moduli field, you've got an isolated minimum at negative energy. In general, when you do this, the energy you get is very small in Planck units. So you have a small negative energy density. Then they tell you to add an antibrane. Adding an antibrane does two things. The first thing, like I told you, is it breaks supersymmetry. The second thing it does is it adds a strictly positive contribution to the vacuum energy. So I started off with something with negative vacuum energy, and then I add a small positive contribution. And then depending on the relative tuning of the negative energy from the ADS and the positive energy from the antibrane, I can end up in a couple different scenarios. If I don't add enough negative energy to overcome the if I don't add enough positive energy to overcome the negative energy of the ADS, I end up with a non-supersymmetric ADS solution. If I add way too much energy, I just totally destroy the solution. We run away to decompactification and we recover 10-dimensional supersymmetric flat space. But if you're very lucky, if you tune things just right, so that the antibrane adds more positive energy than you started with negative energy, but only a little bit more than you started off with, you can end up with a de Sitter vacuum. So the name of the game in KKLT is to tune these two energy scales. It's to tune the negative energy scale of the ADS against the positive energy scale of the de Sitter. Is there a clock in here? Over there. Okay, cool. Thank you. Over there too. Okay, cool. Thank you. So there's a problem, which is that if you just chuck an antibrane into your ADS, it always decompactifies. And the reason is that the energy of the antibrane is set by string scale quantities. It's set by alpha prime. And the energy of the ADS vacuum is set by the EFT scale. So if you've started with what KKLT told you to start with, a scale separated vacuum, where the energy scale of the ADS is much less than the string scale, the energy of the antibrane is always too big. So you have to work a little harder. You need to come up with a way to redshift down the energy of the antibrane. And we know of one really good way of redshifting down the energies of branes, the Randall-Sundrum model. So the idea is to take a Calabi-Yau and engineer a Randall-Sundrum throat in your Calabi-Yau. If you do that, if you engineer a Calabi-Yau with a long throat, then energy scales at this end are exponentially suppressed relative to energy scales at this end. So if you chuck your antibrane here, its energy is artificially shrunk. That's the game we're going to play. We're going to engineer Calabi-Yaus with the Randall-Sundrum throat, and we're going to put an antibrane at the end of the throat. So Giddings, Kotru, Polchinski told you how to get this Randall-Sundrum throat from a Calabi-Yau. You have to work near a boundary of moduli space where the Calabi-Yau becomes singular. You don't want your Calabi-Yau to actually become singular, but you want to be very close to a singular Calabi-Yau. And the scale of this redshifting, by what factor you shrink the energy of the antibrane, is related to how close you are to the Calabi-Yau becoming singular. So I'm going to want the Calabi-Yau to be exponentially close to being singular without actually being singular. And that's what makes doing this hard, is being able to get something that's exponentially close to zero without being zero.
Well, what kind of singularity do you require? Right?
Conical.
Conical singularity.
So let me, oh, sorry.
Yeah, because the moduli, like the Calabi-Yaus are discrete, right? The different types. So what do you mean by close to?
Yeah, that's a great question. So there's a discrete choice of Calabi-Yaus.
Yeah.
Each Calabi-Yau has a continuous moduli space.
Yeah.
Equipped with a natural metric. So you pick your fluxes, that gives you a potential. You find the location of the minimum of that potential, and you see how far in terms of metric distance or some other notion of distance on the space you are from the boundary of moduli space where the Calabi-Yau actually becomes singular.
Okay.
So if I can draw an example of the simplest Calabi-Yau, which is a torus.
Yeah.
The moduli space of a torus looks like this.
Yeah.
And okay, a torus doesn't quite have the right kind of singularity I need, but pretend this was a singular point here.
Yeah.
Let's say I got stabilized there. There's a metric, you can compute this distance, and you want this distance to be small.
Okay.
So in summary, KKLT gives you the following recipe for building de Sitter from a collab EL. You start with a supersymmetric ADS vacuum with a small vacuum energy, a warped throat so I can redshift an anti-brane, and all moduli stabilized. Then I put in an anti-brane at the bottom of the throat, and I hope that the energy scales are tuned such that I get uplifted to de Sitter and not non-SUSY ADS or lower. And KKLT told you if you do all of that, you land on de Sitter. Now, there's an important caveat, which is that every calculation that went into those pictures I just showed you was done in supergravity. So corrections to the supergravity framework that those calculations are done in are important. I'll talk about those later. For now, I'm going to neglect those corrections and trust the supergravity picture. And then at the end of the talk, once I've shown you the de Sitter Vacua, I'll comment on corrections. So I promise I'm not sweeping them under the rug. I just don't want to say modulo corrections on every slide. So today I'm going to do that. I'm going to pick a collab out. I'm going to pick fluxes. I'm going to produce a de Sitter vacuum doing that procedure. And it's the first, we're going to give the first collab out where you can actually do this, where we think the anti-brane uplift works. Why not? Why am I telling you this now and not at any point in the last 20 years since KKLT was written? The sort of simplest reason is our approach for doing this is through large scale computation. And of course, the longer you wait, the better your computers get. But in particular, it's not just, our computers are 1,000 times faster than they were a couple years ago. We've also recently developed a lot of technical computational skills specifically for doing computations with collab-EOWs. So there's now specialized software for dealing with collab-EOWs that lets you compute topological data of collab-EOWs. It lets you compute complex geometry of collab-EOWs. It lets you scan over hundreds of millions of choices of flux vectors in collab-EOWs. There are all these technical developments that myself and others have contributed to over the last 3 or 4 years that are really necessary to make that work. But even all that isn't enough. In a little bit, I'm going to tell you to actually make this work, to actually be able to scan over all these collab-EOWs and found a de Sitter, we had to go and write a math paper to help us better understand how many collab-EOWs there actually are. So to actually do this, to actually solve this problem that's been open for 20 years, it really took a lot of technological development that's only come together in the last few years. I don't think this paper could have been, in fact, I'm positive this paper couldn't have been written in 2019, much less 2024. Oh, sorry, yeah, 2004, yeah. The paper could definitely have been written in 2024. So enough background, let me start telling you what I actually do. So first, let me just say a couple technical words. We work with a particular type of collab-EOWs called toric hypersurface collab-EOWs. Why do we pick these? We pick these because you can put them on a computer. There's specialized software packages that are written for these collab-EOWs that let you compute everything in them very quickly. There's nothing special about these collab-EOWs. I didn't pick them because KKLT works in them and not in other collab-EOWs. I picked them because they're easy to work. It's not enough to pick a collab-EOW. I also need to pick an orientifold, a quotient of the collab-EOW that lets you turn on fluxes. And I need to pick a boundary of moduli space, which I approach to make my work through. So I need to pick 3 types of discrete data before I start specifying fluxes. I need to pick a collab-EOW, a quotient, and a boundary of moduli space. And our search space consisted of 416 of these triples. Where did that number 416 come from? Well, that's why we wrote this math paper. In this big list of collab, so toric hypersurface collab-EOWs come in a big list. And what we started doing was we started scanning over the list. We took the first collab-EOW on the list, we looked for de Sitters. We took the second collab-EOW on the list, we looked for de Sitters. We found that we kept on seeing the same collab-EOW over and over and over again. The same collab-EOW can emit many different descriptions in terms of this toric data. You waste more of your compute time and compute cost doing the same calculation over and over again than you find actually looking through new collab-EOWs. So we wrote a math paper where we used number theory to prove theorems about how many collab-EOWs there are. I think this is really neat. When you go and write papers about cosmology, usually you don't think you're going to prove a theorem in number theory to help you do it. But that's actually what we had to do this. And I think this is a fun example of something I believe very strongly in, which is that physics and math go best when they're together. We did something pretty cool in physics and we had to do real math to do it. And I think that's a fun and sort of powerful situation. That having been said, we have a list of Calabi-Yau's and list of physics. So to compute the potential, the supersymmetric potential, you need to compute these two auxiliary functions, the superpotential and the Kähler potential. The superpotential, I know exactly. It takes this form. It takes the form of one function of the complex structure in axiodilaton and another function just of the Kähler moduli. It splits. And there are not, we don't think there are any other terms here because of non-renormalization theorems that tell you there can't be. The Kähler potential, this is the classical form, it's pretty ugly, and it definitely has other terms that we don't know. The Kähler potential is a double series expansion in alpha prime, the string length, and G string, the string coupling. At string tree level, at order G string to the 0, we know the alpha prime terms. And in the paper, we incorporated the alpha prime terms at string tree level. Beyond string tree level, we don't know anything about the Kähler potential, so we didn't include those terms.
All the Washington tons are included.
So the world-cheat instantons are included, yeah. We include world-cheat instantons in the flux potential and in the Kähler potential, they're mirrored. As many of them as we could compute. And we have pretty convincing numerical evidence that we got enough. So to actually go and compute the superpotential, you need to pick some fluxes. Fluxes for the 10-dimensional gauge field are allowed to thread, you're allowed to thread flux through cycles in my Calabi-Yau because the Calabi-Yau has non-trivial internal topology. You can pick integer flux quanta through your Calabi-Yau, but not arbitrarily much flux. There's an upper bound on how much total flux you can compute. And Gauss' law through the full 10-dimensional space tells you that you can't have any extra flux. There's a total amount, the quotient that I told you about earlier, the orientifold, induces negative charge for these gauge fields in 10 dimensions, and I must have 0 total charge through spacetime. So flux contributes charge for this gauge field, and branes contribute flux to this gauge field. And if I pick a flux vector, I must include enough branes such that the negative charge of the quotient is completely canceled. So this Gauss law is a very powerful constraint. It tells you how much the total amount of flux you're allowed to have is. And actually, if you want to include an anti-brane, it tells you you need to include slightly more flux than you think you're usually allowed to have. There's an important caveat here that I'll mention now. Nobody actually knows whether you're allowed to have even flux or odd flux quanta in a Calabi-Yau. Your fluxes are like some list of integers, and just nobody knows if you're allowed to have even odd integers in your list of integers. For purely computational reasons, we were only able to find solutions with odd flux quanta. We don't actually know if this is a problem or not, but it's a problem that can't be physicsed away at the moment, so it's worth mentioning.
What would be the reason that you can't have odd?
So the reason is that we're measuring flux through the Calabi-Yau. What actually matters is that fluxes need to be quantized in the orientifold. And the question is, do extra cycles arise in the orientifold that aren't present in the Calabi-Yau? So there's this Frey and Polchinski paper where they do an orientifold of T6, and they find an extra, they call it a half cycle, that appears in the quotient that wasn't present in the T6. And the integral of the flux quantum through that cycle is a half. So you need an even flux quantum so that when you divide it by a half, you get an integer.
For all the cycles or just for that?
They have, so for T6, it's very symmetric. They have these for all of the cycles.
Okay.
But their construction actually crucially depended on the fact that there's 1 cycle in T6. The half cycle basically was a 1 cycle.
Yeah.
There's no 1 cycles in a Calabi-Yau, so their proof certainly doesn't apply. That doesn't mean there isn't such a constraint, but it would have to be more complicated than that. People seem to have largely forgotten about this paper until we pointed it out last year, but anyway, I think the situation is still out for threefolds. We think it's a computational limitation on our part that we can't find even flux quanta. We don't see a principal reason why it can't work. It's just, 2 to the H2 1 times harder. Sure. Okay, so what we're gonna do is we're gonna take advantage of the fact that the superpotential splits into a complex structure part and a Kähler structure part. And first, what we're gonna do, this is what KKLT told you to do, though it wasn't clear when they said it that it would actually work this way, is first we're gonna stabilize the complex structure. And then on top of that, we're gonna stabilize the Kähler moduli. So it's a two-step process, and that works because of this split, which we engineer. We pick Calabi-Yaos where this splitting happens, it's non-generic, but we only look at Calabi-Yaos where it happens. And this is the same framework they used to construct the supersymmetric ADS vacua without the warp throat. So this is the same framework that was used in that paper. The first thing we're going to do is we're going to construct supersymmetric ADS with the throat, and then we're going to inject anti-brains and land on the center. So let's do it. Let's engineer a supersymmetric ADS with a warp throat. The first step is to stabilize the Kähler moduli, or the complex structure moduli. So the scale of warping at the end of the anti-brain is controlled by this quantity ZCF, which controls how far you are from the wall of moduli space where your Calabi-Yau actually becomes singular. So in this picture that I drew over here, the green line is this special point, and ZCF measures how far you are from the special point. In a real Calabi-Yau, if the moduli space is higher dimensional, it's a full codimension 1 submanifold of moduli space, but it's part of the boundary. And ZCF is literally just the distance you are perpendicular to it. So you take the superpotential for the complex structure moduli and you expand. You expand it into a part that's singular, that diverges along this boundary, and a part that's smooth along that boundary. Then you use the part that diverges to stabilize this distance, to stabilize how far you are from the boundary. And then you use everything else to stabilize the remaining complex structure moduli, including the axiodilaton. So we've split the superpotential into a complex structure.
The axiodilaton is always hyper, right? So it's in the other. I mean, here in type 2B, right? In type 2B, the dilaton plus string constant, they're always in a hyper.
They're always in a hyper, but I've broken n equals 2 to n equals 1, so I don't have vectors and hypers. Well, I have vectors, but I don't have hypers.
Yes, so but you had a form for the k that was n equals to 2, right? Where you have and the axiodilaton plus the volume of the Calabi-Yau will sit in the T moduli. Not in the C. Right.
So the axiodilaton actually it sits in its own term, and then with the special ansatz we take for the fluxes. So this isn't the generic situation.
Mm-hmm.
We pick special fluxes where it works out this way.
And the volume, though, the Calabi-Yau volume, the alpha that controls alpha prime corrections is in the little t, right?
Yes. Mm-hmm. Certainly, this is not how it works for if I pick a random flux. We pick very special fluxes where it works out this way, where you can pick package tau as one of the complex structure moduli. I have a backup slide with more details about the complex structure moduli stabilization if you want to hear more, but yeah. But the point is that this picture works only for special choices of flux. And the thing that we did that was the hardest, that we spent almost all of our time doing, is finding flux vectors for which this works. But the upshot is, if you can find these special flux vectors, you can stabilize all of your complex structure moduli and the axiodilaton. And the ZCF, the modulus that controls the scale of warping, is given by e to the minus pi over G string. G string is the string coupling. That's stabilized because I've stabilized the axiodilaton, times a ratio of 2 flux quanta, the flux quanta that are related to the throat. So I've stabilized all of my complex structure moduli, and I land on a VEV for the complex structure, for the superpotential of the complex structure moduli and axiodilaton that is always exponentially small if I'm in a weakly coupled regime.
But can you choose, because GS is also a field that has to be stabilized.
Mm-hmm.
So can you stabilize G string GS to be small?
Yep. In our examples, it's about 1/10. If you don't want to uplift to de Sitter, you can get way below.
And it's a 10th because you chose fluxes that contains number 10 somehow.
Yeah, it's just the characteristic scale. We don't pick G string. G string gets set to whatever it is by the stabilization.
But you can have perturbative. You are in the perturbative regime.
Yeah. So there are certainly G-string suppressed corrections to the Kähler potential that we don't know how to compute. We can numerically estimate them from NDA and they seem small. That's certainly one of the corrections I'll talk about later in the talk. We have Vacua where GS is very, very small. I think the smallest I've ever seen is 10 to the minus 5, but I'll tell you why we don't like those in a couple slides.
And again, you're in type 2B, so the matter of the standard model would be in brains that float around, or would it be?
So we are definitely not claiming to engineer the standard model matter content or gauge fields. We just want the positive CC. If you wanted to go and engineer the standard model, that's sure one of the ways you would try to do it. We're currently trying to make it work on top of these constructions. It's difficult to make work, but yeah, that's the sort of the best way we know of to make it work. Another thing you could do is to start with an F theory picture where you have singularities that give you gauge groups and matter content. With Waddy, Taylor, and I, we've talked about doing this, but our method of stabilizing tau is not compatible with that. So it's sort of unclear how to start. But that would be better because then I wouldn't have brain moduli to worry about. Okay, so the game we play requires a special choice of flux quanta, and we found 240 million of these choices of flux vectors. And 141 million of them actually give you minimum for the actually let you stabilize the complex structure moduli. In a certain limit, you need to check convergence of the superpotential at the minimum, and that's generically hard. The thing that basically controls convergence of the flux superpotential is this W naught, the VEB of the flux superpotential at the point where you stand up. This W naught basically tells you everything about how good your approximation is because it controls the size of supersymmetry breaking from n equals 2, where I know everything, to n equals 1, where I don't. And just to give you a spoiler alert, from these 240 million, we're going to get 5 decisions. So that's 5. So that should give you an idea of how hard it is, how many things have to go right. But from these millions of flux choices, you get nice, well-supported distributions in W naught, the VEB of the superpotential, which is basically the square root of the ADS energy, and ZCF, the thing that controls the suppression scale of the anti-brane. So because we have these nice, well-supported distributions, you can have a hope of balancing these against each other. The name of the game in KKLT is balancing those two scales, and because we get so many draws from this distribution, we have a hope of making it work.
These are in 40 Planck units? Or?
These are in 40 Planck units, yeah.
And okay, yeah.
And this is the part where I like to say we didn't set out to make this error. We set out to make supersymmetric ADS with a warped throat. And once we saw these distributions, we thought, wow, maybe we really can make this inner after all. We made the supersymmetric ADS Vacua with the warped throat, the first one, 7 calendar days after we started this project. We made the first inner vacuum 18 months later, which is the relative scale of difficulty of those two endeavors.
Sorry, Richard, are those marks on the right-hand plot, like to the left, like minus 3, minus 16, minus 15, are those tick marks or are those?
No, those are data points.
So there's a kind of weird regularity in a bunch of isolated solutions with many different nodes.
So this is a sort of limited sample of the 140 million. Those we kept because we wanted to see them for supersymmetric ADS analysis. If you take the full data set, it's
Okay, we fill it in more.
Yeah. Yeah, they're there for a reason. They're there because we wanted to see them. Yeah. Okay. I am doing pretty well on time. Cool. So now I've stabilized my complex structure moduli in such a way that I get a warped throat. But I haven't told you anything about what the warped throat looks like. So this is a slice of ADS5. In my Calabi-Yau, I've engineered part of the Calabi-Yau to look like an ADS region. There's an S3 at the tip when the ADS gets cut off. The radius of curvature of that S3 is root GS, the string coupling, times m, the most important flux quantum, times alpha prime. So KPV, the people who computed the potential of the anti-brane at the end of the warp throat, worked in the strict supergravity limit, where alpha prime is 0, or equivalently, where the radius of curvature, the dimensionless quantity is radius of curvature over alpha prime. So if you want, or radius of curvature squared over alpha prime. So if you want that ratio to be, we want to do supergravity, so we want that ratio to be super large. That means we want GSM to be big, if I want to trust supergravity at that point. In the other regime, where GSM is very small, and this radius is very small, there's a dual gauge theory picture, but the KPV calculation doesn't work. I don't know what the anti-brane does anymore. So to really trust the calculation of the anti-brane energy, and therefore really trust what KKLT told us to do, I need to work in a regime where GSM is much bigger than 1. So that this S3 is weakly curved and bulk supergravity is a good description. I'm not going to be able to do that. I'm going to show you examples where GSM is about. I can't produce examples where GSM is 10 or 20 or 100. And I'll comment later on about whether that's an us problem or a fundamental problem. So in this talk, I'm going to pick GSM greater than or 1-ish, and then pretend bulk supergravity is a good description until the end when I come back to correction. So here's the same scatter plot of GSM. So you'll note that we're really strongly localized in the GSM small regime and not the GSM big regime where you want to be. So this is why we don't actually want GS super small. We want GSM to be big enough that we can plausibly claim good supergravity control over what's going on at the tip. You don't need that if you don't want an anti-brane. So for non-SUSY ADS, we regularly get GSM of 1,000th or something like that.
Nature lost a chance. Like being the sitter instead of the sitter.
You know, part of me has always thought that like 40 years, I shouldn't say this if I'm being recorded, but whatever. 40, 50 years from now, the experimentalist will be like, oh, we screwed up, the CC is exactly 0. I think that I don't actually think that, but I think it would be very funny. I think that if we hadn't measured the CC to be positive, probably people would have just said quantum gravity in the sitter is impossible 30 years ago and moved on. But now life is much more interesting. Now we have to think about the hard case instead of just doing everything in ADS. So it's an annoyance, but it's also an opportunity to do something. Okay. So far, the picture for what I've done is I've supersymmetrically stabilized my complex structure moduli in such a way that I have a warped throat inside my Calabi. What I now need to do is I need to supersymmetrically, I'm still constructing supersymmetric ADS vacua with the throat, because that's where KKLT told you to start. That's not the main deliverable, but it's a key step you need towards getting the main deliverable. So now I need to tell you how to stabilize the Kalin moduli. You take this superpotential. So there are these coefficients, A sub D. Nobody actually knows what the values of these coefficients are. There are some papers by Meiki Kim and Ashok Sen and friends, which make progress towards computing it. They write it as an integral over worldsheet modes, and then they can't evaluate the worldsheet integral. They think the answer should be kind of order 1-ish, but for now, what we do is in some units, we take these coefficients to all be 1. And then at the end, once we have the solutions, we scan over those coefficients. And we looked over 7 orders of magnitude and nothing changed. So these are unknown coefficients, but I don't think they're very important unknown coefficients.
What was T sub D? Capital T sub D?
Oh, it's the volume of a 4-cycle.
So the reason these are not so important is that you're in a regime where the 4-cycle volumes are big enough that they're small terms.
What actually happens is as you scale these AD up and down, you move around in big T space to compensate for it. So yeah, you can do that until either you end up in a regime where the Calabi-Yau volume gets bigger as AD gets smaller. No, as AD gets larger, the Calabi-Yau volume gets larger, sorry. And eventually you end up in a regime where the anti-brane energy is too big and you decompactify, or you end up in a regime where you under uplift and end up in SUSY broken ADS. The minimum still exists, it's just that the relative size of the 2 terms changes, but very, very slowly, logarithmically in the size of this coefficient. And to be clear, I said we scanned over 7 orders of magnitude. That doesn't mean it doesn't work outside that window. It means we got bored. Actually, what it really means was string pheno was the next day and we wanted to post the paper. But yeah, it persists outside of that window. That's just the only place we looked. Okay, so to supersymmetrically stabilize the Kähler moduli, we just use Newton's method on this potential. There's nothing really anything that's a super clever trick. You just do Newton's method and see where it takes you. And you find a supersymmetric ADS minimum. That's really expensive because these Kähler moduli spaces are frequently the complex dimension of these moduli spaces is hundreds. So Newton's method in a 100-dimensional space is hard. We've still checked hundreds of cases for Kähler moduli stabilization for supersymmetric ADS vacua with a warp throat. I've shown 5 of them here. These are the 5 that we put in the appendix of the paper. And yeah, these are real vacua. Their cosmological constant, it's negative, but it's, you know, you can get the CC of 10 to the minus 90 in Planck units. So our CC is plus 10 to the 100 minus 120. The CC of these universes is minus 10 to the minus 90. But they're real solution to string theory. If you don't want a conifold, the smallest that we've gotten to so far is 10 to the minus 500 and something. But the conifold makes life harder.
The volume, your final control parameter is large at the end of the calculation.
Yes. It's order hundreds of thousands in these guys and order tens of thousands in the de Sitter in Planck units.
Is there a deep reason why here H21 and H11 are the opposite of the first models that were presented? Because when you look at, say, the quintic in CP4, etc., you have a few H11 and a lot of H21.
Mhm.
Here is the opposite.
It's easier. The hard part is scanning over flux vectors.
Mhm.
So we want our flux vectors to live in a small dimensional space.
So just pick them.
Yeah.
To have this.
We would have loved a case where H21 and H11 are both small, but in the list of toric hypersurface Calabi-Yaus, there's no case where they're both small. If you want H21 to be small, so the flux search finishes, H11 has to be big. So what they actually did in those cases when they started studying flux vacua in not the quintic, but in the 11226 12ic, which is the H21 equals, or sorry, H11 equals 2 thing that's very much like the quintic, they actually found fluxes in the mirror and then made an argument that the fluxes will still stabilize all the moduli in the big H21 side. So they actually implicitly worked at small H21.
The physical origin of these tiny vacuum energies is, well, there's this exponential of e to the minus 1 over g string.
It's the exponential of e to the minus 1 over g string.
And
it's-
that arises again because,
Because we made a special choice of flux quanta.
yeah,
So the flux superpotential, can that side of the room see if I write over here? So the flux superpotential has an expansion into 2 terms. A polynomial piece that's polynomial in the superpotential and the axiodilaton, and an exponentially suppressed piece. And we pick fluxes such that this guy vanishes and everything you're left with is exponentially small in 1 over g string. So everything comes from the special choice of flux vectors. Incidentally, Denef and Douglas had this statistical argument where they argued basically how small of a vacuum energy could you ever hope to find? And it's like dozens of orders of magnitude bigger than these. And the reason is they worked in the continuous flux approximation. The integrality of fluxes is very important in this story because we're solving a Diophantine equation. So the integral nature of the fluxes is super important in avoiding Denef and Douglas. Okay, let's work supersymmetry. Let's do the hard part. So far, everything I've told you has been supersymmetric. I've constructed supersymmetric ADS vacua with these warp throats. It's nice to have them. It's like a look what we can do, but the real reason we want to do that is we want to throw in an anti-brane and get a de Sitter. Oh, sorry, let me say one more thing. So KKLT, the next year, they had a follow-up paper with McAllister and Maldacena, where they took a ADS vacuum with a warped throat, but no anti-brains, added a brain anti-brain pair, and used the attractive energy of the brain anti-brain pair to drive a period of inflation. This brain anti-brain inflation model requires some very carefully tuned initial conditions, even more finely tuned really than the de Sitter vacua. We, by happenstance, lucked into a model where all of their conditions are exactly satisfied. We can't actually do the inflation because you need the numerical metric on the Calabi-Yau, which we don't have, but it's a neat observation.
Or what is K prime again?
Oh, sorry. K prime is a dressed form of the flux through the dual conifold cycle.
That's why it could be fractional.
Exactly. When I wrote, this is really K prime up here. K prime is the dressed quantum that ends up in the real formula for ZCF if you're very careful. Okay, so far everything has been supersymmetric. Let's be really ambitious and break supersymmetry. So the problem with doing that is the tadpole bound, Gauss's law. I have to have zero total anti-brain charge. I have to have zero total gauge charge through 10 dimensions. So if I want to include an anti-brain, that means I need one more unit of flux than what I'm really supposed to have in the absence of anti-brains. So let's do it. Sorry, was that a question over there? No, okay. Let's do it. Let's look for flux vectors such that you have one extra bit of flux than you need so that you have to have the anti-brain. I don't want regular D3s and anti-brains moving around because those are going to attract each other and destabilize. I want a single anti-brain and nothing else. So I want exactly one unit of flux more than the usual Gauss's law says I can have. Okay. So what happens when I have an anti-D3 brain? What actually does the physical geometry do? The warping, the effect of the throat, pulls the anti-brain down. So the anti-brain sort of naturally wants to sit at the bottom of the throat, but there's an entire S3 at the bottom of the throat. And the warping pulls it to sit at the bottom of the throat where the S3 lives, but warping alone doesn't tell you where the anti-D3 sits along this S3's worth of angles into the tip of the throat. There's a calculation by Kotru, Pearson, and Verlinde that tells you what the anti-brain wants to do. And the answer is, as long as there are these 12 units of flux through this cycle for each anti-brain you have, the anti-brain finds a happy minimum at the bottom of the throat and sits there. It will eventually tunnel out of that minimum. It's a positive energy minimum, so it will eventually tunnel out. But as long as it sits in this minimum, it contributes a constant positive energy to the total potential of spacetime. That's the behavior I want. So I'm going to restrict to choices of flux vectors that have a single anti-brain and therefore at least 12 units of flux through the conifold. It's hard to put a lot of flux through this cycle. So I want to only look at one anti-brain so that I only need 1 unit of flux instead of 24 units of flux. By the way, this is why we have to have odd flux quanta. If you only restrict yourself to have even fluxes, you need 2 anti-brains. That means you need M of at least 24, and we just can't do it. It's too hard. It's too hard computationally. Not it's too hard physically. It's fine physically. It's just computationally we can't find it. And then the usual caveat applies. KPV is a supergravity calculation. You only trust that in the regime supergravity is good. We're going to end up sort of in that regime. So we want flux vectors with 1 anti-brain and 12 units of flux through the conifold. That's really hard. Of our 240 million, 33,000 are of this form. So that means we have 33,371 chances to find de Sitter. Okay, now, so far everything I've told you isn't enough to actually find de Sitter because I haven't engineered the tuning. I've fixed the W naught and I've fixed the ZCF, but I haven't given them the right size. I've introduced the negative energy and the positive energy, but I haven't said anything about whether their sizes are like each other or not. So here's the ratio of those two energies. The ratio of the anti-brane energy to the ADS energy is this incredibly annoying numerical factor of 179 times the Calabi-Yau volume times the Calabi-Yau volume to the 2/3 times some complex structure stuff times z to the 4/3, z being the thing that sets the scale of the throat, divided by W naught squared. And I want this big ratio to be just barely more than 1. 1.1 is okay, actually 3 is fine, 5 is right out. So somewhere around 2 to 3 is okay. So that means that I need Z to be tuned relative to W. Nobody before us that we could find anywhere in the literature had ever been careful enough to get all the numerical factors and everything. This numerical factor is 100,000. So it's actually a really important numerical factor to get the tuning right. If you just say you need Z to the 4/3 over W naught squared to be close to 1, you've actually made the problem seem much easier than it is because of this really large numerical factor. So I actually think one of the most important things we did was compute this numerical factor, because without it, we have no idea if we're right. So that's the name of the game. The name of the game is sample enough choices of flux vectors until by happenstance, you land on this ratio being close to 1. So remember, Z is e to the minus pi times k prime, this flux quantum, divided by GSM. We want Z to be really small, so that means we want K to be big. But now we've got a real serious problem. And our real serious problem is that all of the limits we want, generically, you can't satisfy them all. We want W naught to be small, so that everything is well controlled and we trust some of the series expansions we're making. We want GSM to be big, so that supergravity is a good description of the anti-brane and we can trust KPV. And we want Z small. You can't do all of these generically, it's too hard. These three requirements are in tension. W naught is e to the minus 1 over G string, so you want G string to be small. But then GSM has to be big, so you need M to be big. But then Z is e to the minus K over M, so you need K to be big. And the product of Km is bounded from above by the Gauss's law. So you have these three intersecting limits that are mutually incompatible. It's really hard to get to sitter space. A lot of things need to go right. But we did. We were able to find 5 cases where, so these are the 33,000 things, and these are their W naught, and these are their Z's. And this little band is the band of window where the alignment, the ratio Z to the 4/3 over W naught squared with the dressing, comes out order 1-ish. Things in this window have a chance of being de Sitter. But if you look at this window carefully and you look at the GSM of things in this window, GSM is almost always small. So that's the problem. It's easy to get W naught small and ZCF small, but then GSM is small and you don't trust the KPV calculation. So this graph just really shows why these three things are difficult. And all of the de Sitters live in this cluster over here. No, sorry, this cluster over there. But we did. We found 5 flux compactifications whose effective potentials have de Sitter minimum. So these are the inputs. These are the discrete dials you can tune. You can discretely pick Calabi-Yaus, and you can discretely pick flux vectors in your Calabi-Yau. And from those discrete data, you get the continuous parameters. You get the string coupling, you get W naught, the VEV of the flux superpotential, you get GSM, the radius of curvature of the tip of the throat, you get ZCF, the relative suppression factor of anti-branes at the tip of the throat, and you get the vacuum energy. And these 5 guys, they have positive vacuum energy. So 20 years after KKLT told you to do this, we did. We finally found it.
And you also proved that 0.746 is much larger than 1.
Exactly. No, we did it in a truncated theory where we neglect these corrections.
And again, for all these models, the alpha prime corrections are small because the volume of the Calabi-Yau is big.
So alpha prime corrections to the Kähler potential are, so we incorporated the ones at string tree level, we included their effect. So they don't need to be smaller, otherwise we just did them. At string loop level, there's 2 suppressions. One is the G string in front. G string is like a 10th. And then there's I guess it's like a 20th, more like in these examples, but and then There's also suppression from the Calabi-Yau volume, like you said. So those are sort of doubly suppressed. Naive dimensional analysis tells you it's like an order 10% correction. Alpha prime corrections to KPV, on the other hand, very different story.
Sorry, the previous table you showed with the vacuum energy, that was like 10 to the minus 90. There were a few
Yeah.
candidates. Wait, sorry, what's the difference between that and why these are so much larger?
Yeah, good. So those were supersymmetric ADS.
Uh-huh.
I didn't need to do two things. I didn't need to arrange tuning of scales between the length of the end of the length of the throat and the energy of the ADS. And I also didn't need GSM to be bigger than 1 because I wasn't doing anything at the tip of the throat. The tip of the throat is just some region of space-time where something happens, who knows what happens, but away from that region, you just get Einstein's equations. Here, I'm putting an antebrain in that strongly warped region. So I want that region to be the smallest curvature possible. Okay, and let me say the elephant in the room, which is that we got the plus sign, but the CC is 100 orders of magnitude too small.
Too big.
They're too big, yeah, too big, yeah. Sorry, too big, definitely. Yeah, I would have rather landed on CCs that are 100 orders of magnitude too small, but no, the CC is 100 orders of magnitude too big. It feels like the plus sign was the hard part. The plus sign was the part that was qualitatively new, but yeah, who knows?
And these are just 2 different Calabi-Yaus you're looking at?
These are actually 5 different Calabi-Yaus.
Okay.
We don't understand why we only found these 2 Hodge pairs, even though there's different Calabi-Yaus in each of these Hodge pairs. But indeed, they're different Calabi-Yaus. In fact, this Calabi-Yau has 22 de Sitter vacua, and this Calabi-Yau has 5, and these have 1 each. We understand why these have 1 each and these have 22 or 5. We don't understand why they all worked out that they have the matching Hodge pairs. So people have been trying to do KKLT for 20 years, and I think this is far and away the biggest step anyone has taken towards doing KKLT. It's not clear we've done it, but it is clear that this is a tremendous step towards actually doing it.
It's not clear you've done it because GSM is around 1.
Yeah,
No,
exactly.
yeah.
Okay. So I showed you the schematic plots of KKLT earlier in the talk. This is what it looks like in an actual example. So this is the energy of the ADS. You've got the isolated negative energy minimum, and there's the energy of the de Sitter, positive. In de Sitter, you're not allowed to have tachyonic modes. All of your particles have to have positive masses. We computed them. We computed the masses of all of the moduli fields, and here they are. In this example, the H11 is 5, H11 is 93, H21 is 5. So that means there's 93 plus 5 all times 2, because they're complex scalars. There's 196 real scalar modes, and here's their spectrum of masses. They're all positive. You can count the deaths.
And so H is the Hubble.
Yeah.
So they're still very small, very light. Yeah.
They're light in Planck units. They're heavy in EFT units. Well, heavy-ish in EFT units.
Well, the H is 10 to the minus 20.
And these guys, H is 10 to the minus 10 in Planck units. So they're light in Planck scales, but if you build a de Sitter sized ruler, they seem heavy.
Okay, so your de Sitter still has a large cosmology, much larger cosmological constant than now.
100%. 100%. Yeah. 100 orders of magnitude too big.
Like 10 to 98%.
Yeah. 100%. The answer to your question was yes. Not yeah. And here's the other 4. They look pretty similar. So let me make before I talk about the okay, I have 3 minutes left, so I'll make my side comments at the end. Do you trust these vacua? We took the full action of string theory and we truncated. We included all of the terms that are known. We don't think known to us. We think all the terms that are known that all the people have computed, including the numerical prefactors. But what about the unknown corrections? Do they destabilize these vacua? Well, we don't know. But we think we know what all of the unknown corrections can possibly be, and we think we roughly know how scary they are in order. The scariest, by far, the one that almost made us not publish this, was alpha prime corrections to KPV. I showed you on the other slide, GSM is 0.7, and the biggest example is 1.05. Our internal threshold for publishing was we wanted one example with GSM bigger than 1. We ended up getting 1.05, and we said, okay, good, but not really good. That's the scary one. And it's really scary because there's sort of a fundamental bound on how good you can do on GSM. The tadpole bound really puts a hard upper limit on how big GSM squared can ever be. GSM squared is what some people have argued the actual figure of merit for these corrections are. I would say the jury is still out on how big GSM squared really has to be. There's a paper that claims to have computed the size of these corrections. If you take their calculation literally, they say that the tension of a single antibrane is negative infinity. So I think really what they showed is that perturbative treatment of these corrections isn't correct. You need like a string field theory calculation or something. These are the scary corrections. These are the ones that could destabilize our vacuum. I mean, there's the flux quantization conditions. Like I said, in T6 orientifolds, you're definitely not allowed to use even flux quanta, but the proof is built on the topology of T6, which is qualitatively different than the topology of Calabi-Yau threefolds. Nobody knows whether that's true or not of Calabi-Yaus. If you want purely even fluxes, you need at least 24 units of M flux, and we can't get it. Our code just isn't good enough to get M bigger than 24. So that's why we don't have even fluxes. I don't think there's a fundamental obstruction. The bounds are such that you could get the same order parameters I showed with M bigger than 24 and purely even fluxes. We just weren't able to do the calculation because it's harder. G-string corrections to the Kähler potential. We've spoken a lot about them. They're important. Nobody knows what they are. Naive dimensional analysis tells you that it's a roughly 10% correction, which you may or may not be scared by. But in principle, with extra computational power, within the fundamental bounds set by the Gauss's law, we could do an order of magnitude or two better in W naught or G string, and then these corrections would get smaller. The Calabi-Yau volume would get bigger, G string would get smaller. The correction, which goes as like 1 over G string e to the minus 2 pi Calabi-Yau volume would shrink by a lot. So these corrections, they may or may not destabilize these vacua, but they don't put the whole enterprise at risk. Unlike alpha prime corrections to KPV. Alpha prime corrections to KPV coupled with Gauss's law really could just kill KKLT as an avenue, as a research topic. That wouldn't mean de Sitter is impossible in string theory. It would mean that you wouldn't be able to get it the way KKLT told you to. And I think that's the qualitative difference between alpha prime corrections to KPV and loop corrections to the Kähler potential. The metric, the physical metric on the Calabi-Yau isn't the Calabi-Yau metric anymore. It's the warped metric. That's why you have this warped throat. We had to compute the volumes of 4 cycles in the Calabi-Yau. Those volumes were computed in the unwarped metric. Nobody knows if the site of the volumes are appreciably bigger in the warped metric. Again, the numerical analysis, dimensional analysis says that this should roughly be a 10% correction. You may or may not be worried about these. It's not unreasonable to be worried about them, but I don't think they would rule out KKLT as a topic. This is the singular bulk problem, by the way. And to do this, you need to machine learn the warped numerical Calabi-Yau metric. Discussions are ongoing about whether this is plausible or not in these vacua, but we know sort of how it should be attacked. It's just unclear if it's currently feasible.
Here you mean really the metric of the Calabi-Yau, not of the moduli of Calabi-Yau.
No, the metric on the Calabi-Yau. The moduli space metric we know. Well, we know, so G-string corrections to the Kähler potential will deform the metric on moduli space, but we've consistently computed the metric as derived from the Kähler potential we used. The metric on moduli space is 2 derivatives of the Kähler potential. We explicitly took those 2 derivatives of the G-string tree level alpha prime corrected Kähler potential.
Okay, but this is still the metric on the moduli. So I don't understand if this is really the space-time metric of the 6-dimensional.
Yeah, no, here in this bullet point, I'm really talking about the metric on the 6-dimensional guy.
Which is not Calabi-Yau even in the absence of fluxes and warping because of alpha prime correction.
Right. So people have machine learned the Calabi-Yau metric, and people have machine learned the alpha prime correction for the Calabi-Yau metric. And those corrections were seen to be very small. The ones you get from the worldsheet. Okay, and finally, we don't know those AD coefficients in the superpotential, but like I told you, they don't matter. We scanned over 7 orders of magnitude and nothing changed. And we got bored after scanning over those 7 orders of magnitude. It's not like we think something fundamentally goes wrong. Okay, so that's what I wanted to say. I think that whether or not string theory really has de Sitter solutions is a sort of core problem facing string theory as a field. It's like, I would call it basically the question of string pheno. Can you get us out of string theory? The most well-studied way to do this is KKLT. And I think we've taken a pretty big stride towards actually doing KKLT, towards seeing whether KKLT can be done in practice or not. I'm certainly not claiming we have absolutely constructed de Sitter vacua of string theory. There's some big unknowns that need to be understood a little bit better. But I think we've taken big strides towards being able to answer that question. So that's what I wanted to say, and thank you very much.
So I think you said it before, I just wanted to know, vector bundles, low energy spectrum, this kind of thing. Can you put this on these kind of backgrounds? Do you have any idea?
So we know what the low energy spectra of these models are. We know the masses of the lightest modes. We know the gauge fields. We know the couplings. Those are all controlled. But we can only get abelian gauge theories. We can't get the standard model gauge group or anything like that. The way we stabilize the complex structure moduli makes it sort of hard to see how most of the most well-studied way of getting non-trivial gauge groups can be combined with this. But yeah.
So it might be inconsistent with, phenomenologically relevant gauge bundles. Is that a possibility?
I would say that our approach might be inconsistent, but we weren't trying to answer that question. We were trying to answer the question, are there de Sitter vacua? I think we should answer the easier part of the question first and then try to make it harder for ourselves.
So, but this, if it works, will kill the Sitter-Swampart conjecture, right?
That's the $1 million question. Yeah, no, so the version of the conjecture that reads string theory has no de Sitter vacua, yes, it would kill that conjecture. The evidence for that conjecture is that in the corners of moduli space where computations are very easy to do, it's essentially been proven that there's no de Sitter vacua. So that's true. That we can't disprove because it's a fact. The question is, do you trust calculations done all the way out in the borders of moduli space with extended supersymmetry to tell you what happens in cases with no supersymmetry? I say no. I don't see what you're supposed to learn over here to tell you about in the deep interior of moduli space. So if these are real, then we've disproven the conjecture that there's no de Sitter. But there are theorems that there are no de Sitter in certain corners, and those are of course consistent with this because we just don't work in those corners. Yeah.
Is there a way you would, so all of the de Sitter vacua that you found have roughly the same order of magnitude? How do I make up this 100 difference?
Yeah, that's a great question. I think the answer is that in the particular framework we're working in, you probably cannot. And the reason is because of Gauss's law. There's not enough total flux you can put. In the closely related language of F theory, which is the 12-dimensional strong coupling limit of 2B string theory, you can put a lot more flux. You can work with these things called Calabi-Yau fourfolds, and those you can eat a lot more flux on. They're much, much harder to work with. So we currently can't do the calculation there, but yeah.
Wait 20 years and get a better computer.
Wait 20 years and hope that we understand F theory a little better. There's physics to be done more than computing to be done. But let me actually make one more comment. So a thing that sucks really badly is the fact that where's the formula I need? No, I'm just going to write it on the board. So I showed this formula, which is Z is e to the minus I K over GSM. A A thing that sucks is that there's no numerical factor in front of this pi. If you could engineer a slightly different kind of conifold, a calabi-yau with one, our calabi-yaus all have two conifolds. I didn't talk about this, but it's true. If you could engineer a calabi-yau that only had one conifold, then you would put a 2 here, and then you could easily get down to 10 to the minus 70 or 80. Still not 120, but much closer.
By two conifolds, you mean two conifold singularity for modular space?
No, I actually mean just that the physical calabi-yau has two throws.
You talked briefly about inflation and KKLMMT, I guess. So to realize that, would you have to redo all these computations, or do you think you have enough ingredients to put like the active brain pairs and?
Good, great question. So for KKLMMT, we would take that solution, that minimum. And if we had the numerical warped metric, we could just follow the KKLMMT procedure to compute the potential and see what the anti-brains were going to do. We wouldn't need to find new Vacua or anything. That one is beautiful. It checks all the boxes. Let me tell you about a different way you could try to do inflation, which is what I'm doing right now with Matt and Kemi. So we're doing what's called moduli inflation, where you only still have one anti-brain down at the bottom of the throat, but you don't start off at the minimum. You start off away from the minimum, you let the moduli fields, these scalar fields, roll towards their minimum. And as you do, things are evolving, the universe is changing shape, and in fact it inflates. Still up in the air exactly what inflation looks like and how many E-folds you can get, but yeah, that's literally what we're working on now.
You question about the absolute value of this, like the Z, like getting 10 to the minus 120. Like I thought, like the cosmological constant problem is like you have, it's more of a tuning issue, right? I mean, where you have some constant in the, PR Einstein's equations, then you have all these field values, and as standard model goes through all these phase transitions way below, these string scales, these eventually have to exactly cancel out what's in like Einstein's equation. So like when you say you need 120, I mean, isn't it maybe more of a tuning thing? And then at the same time, like, how do I understand like these values in relationship to the Einstein's, the lambda and Einstein's equations versus like all the contributions from the standard model?
Great question. Great question. So I am not trying to solve the CC problem.
Right.
I am trying to get de Sitter Vacua. These Vacua, because I know everything, I know what the effective action looks like. I know what the classical cosmological constant is. And it is that. V naught enters into Einstein's equations exactly as the cosmological constant. It's like if you series expand in modes around the minimum, you get V naught as a constant term in the action cosmological constant. The cosmological constant problem as such is, why do loops of standard model fields not overwhelm this?
Right.
That's sort of orthogonal from what we're doing. We're talking about a bare.
Right, but you don't need then you don't need this to be 10 to the minus 120 though, right? I mean, you just need it to tune that part.
Oh, but nobody knows how to do that anyway, right?
Yeah, but I mean, it's a different issue though. Like,
Yeah, so we call this a toy version of the cosmological constant problem. I myself personally was much more motivated by the plus sign than the minus 120. I think that's the okay. If we could get 10 to the minus 120, that would be great to go and write a Quanta article about, but like I don't know how much scientific advancement that would come over this 10 to the minus 20. The plus sign is the conceptual knowledge.
But I guess a version of that question is, if you just naively in effective field theory think about the effective loops of the massive moduli that you do have. I mean, what's the scale of supersymmetry breaking, I guess, is really the question for those moduli.
It's like Z.
It's like Z.
Well, sorry, Z is the scale of the breaking of all supersymmetry.
Well,
Like
that's-
Z and Planck, basically.
Yeah.
Yes,
So-
Z to the 4/3 and Planck, but
Okay,
yeah.
so just order of magnitude, do you expect corrections to this V naught that are large compared to V naught or not?
I don't see why they shouldn't be there.
Or they shouldn't be.
Why they shouldn't be there.
So loop corrections from just standard effective field theory, the fact that you have a non-supersymmetric effective field theory would be larger than this V, it could either be positive or negative depending on fermions versus bosons.
Well, because the spectrum is preserved by, actually, sorry, let me address that question slightly differently. The spectrum is controlled by supersymmetry.
Right.
So you have, boson fermion pairs.
Yeah, above the breaking scale, right, so you
Yeah.
expect lambda Suzy to the fourth correction.
Yeah.
So the question is, how big is that compared to this V naught?
Yeah, I don't think it should be bigger than this V naught. I don't think it should flip signs, but yeah. I certainly don't think that I haven't thought carefully about what the actual size of those corrections should be.
I mean, somehow they should have been included in what you did, because those are, string loop corrections or.
So we were very careful not to ever do any string loop corrections, because then you would need loop corrections to the Kähler potential, which we don't know.
Right, but you know that the loop corrections are suppressed.
We know that the loop corrections are suppressed in the Kähler potential. We don't necessarily we haven't thought carefully about what they look like in the low energy effective action once you start doing like fermion loops. I guess everything should be controlled by the Kähler potential in 10 dimensions anyway, because that's what you have. That's the point of string theory, right? Is that from the top down, you know everything. So I guess if we believe that loop corrections to the Kähler potential are suppressed, we should believe that those loop corrections are suppressed, but I haven't done a calculation.
Let's thank Richard again.
Good, everyone.
Thank you. Thanks for the talk. Cool.
Just one little sentence. So you're imagining to have this additional effect like two, you're imagining there is a other kind of singularity on the compound, on the Calabi-Yau, or in the